Alright, welcome everyone back. Here we are in section 3. This is higher order derivatives, acceleration, and concavity. This is the last section here that we're covering in chapter 5. Unfortunately, there are two parts to it, right? So we're here in part A. And like I mentioned jokingly here, right, we've seen that taking derivatives is pretty fun. So if you want twice as much fun, take twice as many derivatives. That is, we're going to bring up this idea of the second derivative. So second derive with a V and everything, derivative. There we go. Is the derivative of the derivative. So if you, we're going to take the derivative of the derivative function, and this is denoted in two different ways. So if you use the Leibniz notation, this would be d squared or d2f over dx squared, if you'd like. Or equivalently, we're going to use kind of more often this f double prime of x. So again, this is the derivative of the derivative. This tells us, right, how the rate of change is changing. I know, it's like a dream within a dream. All right, so shockingly enough, right, there are real-world applications that to taking multiple derivatives. And arguably the most important is acceleration. So that's why we have that even in the title, acceleration and concavity. From a more mathematical perspective, right, this second derivative describes concavity. So let me first tell you what concavity is, and then I'll relate it to the second derivative. So first of all, a function is considered concave up at a point, x equals c, if f of x lies above its tangent line near c. Likewise, f of x is called concave down. So those are the two types of concavity, concave up, concave down, at x equals c if it lies below its tangent line near C. And then finally, one more definition I need to give you, a point, which should be in the domain of f of x, where the graph changes concavity from concave up to concave down, or from concave down to concave up, etc., right, is called a point of inflection. Sometimes I would just refer to this as an inflection point. So at this point of inflection, the second derivative is either 0 or undefined. Okay, we'll see how we use that here in just a little bit. So these are the definitions. Let me show you what they actually look like, right? So I'm going to show you concave up and concave down, what they actually look like. So concave up looks a couple different ways. This is one example right here. Notice that if you were to draw its tangent lines at any of these points, tangent lines, just barely skimming it, you should see that for the most part, the blue line, the function, always lies above its tangent line. Right? So this green lines, any of these here, it lies above. So all of these points, the function is concave up on. Another example, functions that look like this. These are also concave up. If you were to draw its tangent line, you can kind of see it lies below the actual function. Okay, the function lies above its tangent line. So this is another example, concave up. So these two pictures right here make concave up. Concave down, something like this. This would be considered concave down. I'll use pink here, or I guess red maybe. And you can see the function lies below its tangent line. So I'm just drawing lots of little tangent lines. You see that the blue function lies below the tangent lines. Another example of concave down would be something like this. Again, it lies below its tangent lines. Notice that concavity and increasing, decreasing, right? So increasing was this idea about somehow it relates to the first derivative, right? we can see that both of these first two right here, they are both increasing, right? So concave up or concave down can both be increasing. Likewise, concave up can be decreasing and concave down can be decreasing. So these are independent ideas. We need to kind of hold these things separately. That increasing and decreasing and concave up, concave down are independent from one another. You can have either or. Okay, and then finally an inflection point, someplace where you switch concavity. These are going to look something like this. Let me actually draw this in black. So the claim is this right here is going to be an inflection point. Quite often I denote it INFPT, right? Inf point. So that's an inflection point. And so we can see down here, the function is concave up. It lies above its tangent lines. And then past that point, the derivative is concave. Sorry, yeah, the function is concave down. It lies below its tangent lines. Likewise, so this is a switch from concave up to concave down. If you do something like this point right here, also an inflection point, I guess. This is where you switch from concave down, so below its tangent lines, to above its tangent lines. And so I draw these here very suggestively, but I wanted to show you kind of in a more robotic sense, right, the concavity. So I went ahead and graphed some of this stuff, actually a function that looks a lot like this one right here, with Desmos, right? So here it is, a function, and we can see that this black dot right here, this is probably going to be an inflection point. But let me go ahead and graph the tangent line. So here's a little tangent line. Remember, you're just looking near this point, right? So in our definitions, we're always near C, right? So I'm just looking near this, and you can see at this point, the graph lies below the tangent line. So I'm going to just take this, I'm going to drag it, right? And it seems to stay below it. It gets a little closer, right? Because this kind of starts looking like a straight line, but it's still below the tangent line. Below the tangent line. Here you can really see, it looks really nice. That's below the tangent line. Still below, still below, still below, and then all of a sudden right past there, look, now the graph, this curve right here, is above its tangent line. Above its tangent line, above its tangent line, above its tangent line. Again, it's kind of straightening out. You can barely see, but if you were to zoom in a lot, the claim is it would still be above its tangent line, just barely. You can see the blue dotted line is below the red line. So this is a case where you would have, again, like I mentioned, an inflection point, and it switches from concave up, it's above its tangent line, to concave down, so here's concave up, concave down, it's below its tangent line. Okay, so hopefully you can kind of see now more clearly concave up and concave down. Okay, so let's go ahead and actually try to apply this stuff a little bit. Like I promised you, the concavity relates to the second derivative. So let me tell you how here. So a function f of x is concave up over an interval if its derivative is increasing over that interval. Derivative is increasing. Well, that's telling you something about the second derivative, right? How the derivative is changing. So in that case, the second derivative is positive, right? So concave up means second derivative positive. A function is concave down. Oops. Concave down over an interval if its derivative is decreasing on that interval, in which case the second derivative is negative, right? So derivative is decreasing. This is saying how is the derivative changing? Well, it's changing negatively, so therefore the second derivative is negative. Okay, so let's try to apply these things. Like I said, the big application here is acceleration. So we'll do one example about acceleration and one example about concavity. So an object is moving horizontally, according to this law here, 10 minus 6t squared plus t cubed. Its position here is given in feet, and t is in seconds. When is the object not accelerating? So this says here, not accelerating, that means that acceleration would be equal to 0. does that mean that the object is standing still? So we'll explore that here in a little bit, but we'll solve this mathematically, right? So this is talking about velocity. Is velocity equal to 0? Because if velocity was equal to 0, then it would be just sitting still, right? Okay, so the first thing, I need to calculate out acceleration. Like we've seen, acceleration is the second derivative. So if you have, velocity is going to be the first derivative of position, and that's going to be negative 12t plus 3t squared. We could talk about the units here, right? The derivative is going to be feet per second. There we are. And then we could talk about the acceleration, which is going to be the second derivative, aka the derivative of the derivative. So if I take the derivative of velocity, I'm going to get negative 12 plus 6t. And this is going to have units feet per second, right? A little bit confusing. Usually you say feet per second squared. So because you're dividing by 2 there, so it's feet per second squared. So those are the units for acceleration. And so the first question that we have, when is the object not accelerating? Okay, when is the acceleration equal to 0? So I'm going to set 0 equal to our acceleration function. And we can solve this. 12 is equal to 6t, therefore t is equal to 2. Of course, include units anytime you can, so this is going to be 2 seconds. I'll just put it right down here. I didn't leave myself enough room. So at 2 seconds, the object is not accelerating. So the question is, how does this influence velocity? Can you have something with positive or negative velocity that's not accelerating? And so let's go ahead and take a look here. So at t equals 2, so I'm going to figure out the velocity at the special time, 2, when it's not accelerating. And so I'm going to plug it back in, right? Here's our velocity equation right here. So if I plug it in, let's see, negative 12 times 2, that's going to be negative 24. And then 2 squared is 4 times 3, that's going to be 12. So that's going to be negative 12, and our units are going to be feet per second. So it's definitely not sitting still, right? So does that mean the object is sitting still? No. In fact, it is moving 12 feet per second in the negative direction. Direction. So again, the first derivative and the second derivative are kind of independent from one another, just like concavity, increasing, decreasing, right? You can have positive or negative velocity and still not be accelerating, right? So in this case, it'd be like moving at a constant negative 12 feet per second, and that's not changing. Still negative 12 feet per second, negative 12 feet per second, negative 12 feet per second. So you have a negative velocity, but it's just not changing, right? The acceleration, how the velocity is changing, is 0. Okay, there is that example. Let's try a little more complicated of one. So the function 1 over x plus 1 over x squared, we want to know where is this concave up, where is it concave down, where can we find inflection points? So remember, back here, inflection points, at a point of inflection, the second derivative is either 0 or undefined. So a lot of what we're going to do is following similarly to what we did in 5.1 with critical points, but now we're going to do second derivatives. Let me show you what I'm talking about. So I'm going to calculate out a second derivative because that tells me something about concavity. So in order to start taking derivatives of this thing, let's remind ourselves that it's useful to rewrite this. Instead of 1 over x, I'm going to write x to the negative first power. And instead of 1 over x squared, I'm going to write x to the negative second power. So this is an equivalent algebraic form for this over here. And now I'm well set up to take derivatives, right? Because I can clearly see now power rule. So, okay, f prime of x, and I'm going to draw maybe a little line for myself, f prime of x. If I take the derivative, the negative 1 comes down, and I reduce my power by 1, so I'd get x to the negative 2. Minus, the 2 would come down, right? So the negative 2 comes down, x to the negative 3. So that's the first derivative. Second derivative, I need to take the derivative of that, the derivative function. So the negative 2 would come down. Negative 2 times negative 1 would be 2. Reduce power by 1. And then, let's see, negative 3 would come down. Negative 3 times negative 2 would be 6, x to the negative 4. And I want to know, when is this 0 or undefined? So actually, I'm going to go ahead and rewrite it in my fraction form. So I'm going to have 2 over x cubed plus 6 over x to the 4th. And so you can see that it's undefined, right? One place that we could have critical points is at x equals 0. But actually, x equals 0 isn't in the domain of the function, right? So it should make sense in the function. So x equals 0 cannot be an inflection point, but we still need to take it into consideration. Let's figure out when this is equal to 0. So I'm going to go ahead and set this equal to 0. That's another way that we can get critical points. So here we go. It's supposed to be a 4 there. Let me subtract this to the other side. So negative 2 over x cubed is equal to 6 over x to the 4th. Let me go ahead and do a little bit of cross multiplying here. So if I multiply this x to the 4th to the other side, I'm going to get negative 2 x to the 4th. Oops, let me scroll up a little bit. X to the 4th divided by x cubed. And so you can see there's going to be quite a bit of cancellation. 3x is down here, 4x is up here. So we're going to have just one x in the top left over, equals 6. And so if I divide through by negative 2, I get x is equal to negative 3. So that's another potential inflection point, but I need to see that you actually change concavity. So just as before, in 5.1, we were trying to find minimums or maximums, I'm going to draw a number line. But in this case, our number line is going to be plotting information about the second derivative, because I want to check about concavity. And so I'm going to plot this point, negative 3, but then I also have to be careful around 0. So this is a place where the second derivative is undefined. So I need to see, does it change concavity around 0? So this is why I kind of plot these two things. Okay, so let's go ahead and plug in some numbers. So my test points here, I'm going to choose maybe negative 4, negative 2, and that's in this range, and then maybe 1, something like this. And remember, I'm plotting information about the second derivative, so I'm going to be plugging in here. Actually, let's maybe look at this one instead. Okay. So now I'm going to pull out my calculator and start plugging these things in. Whenever you have to plot multiple points, negative 4, negative 2, 1, it's a good idea just to use the table. So I'm going to do y equals, this is some stuff from earlier. And so I'm going to plot 2 over x cubed plus 6 over x to the 4th. Okay, and now I'm just going to look at my table. And we can see at 0 there's an error, right? And hopefully at negative 3 we have it 0. Good. So at negative 4, positive or negative? Well, it looks negative to me. So I'm going to go ahead and put negative. Okay, next up, at negative 2, positive. And at 1, let me go down, 1, it's 8, definitely positive. All right, so now we are ready to answer our question, right? Where is it concave up? We can say f is concave up on, so I do con up on. So it's con up anywhere the second derivative is positive. So from negative 3 to 0, we have to be careful to exclude 0. That's why we took this into consideration here, right? Because at 0 it doesn't make any sense. At 0 I'd be dividing by 0. That's a big issue, right? This isn't in the domain of the function. So f is concave up anywhere between negative 3 and 0, and anywhere bigger than 0. F is concave down, con down, anywhere less than negative 3. So from negative infinity all the way up to negative 3. That's where it's less than 0. Okay, inflection points. Where does f have an inflection point? F has inflection point. Remember, this is anywhere that we change concavity. So it needs to be in the domain of the function, and it needs to change concavity. So especially here at negative 3, notice this is in the domain of the function. You're not dividing by 0. You're not taking the negative of a square root, anything like this. And it changes concavity. It changes from negative to positive. So at negative 3, we have an inflection point. F has inflection point at x equals negative 3. Now, it doesn't have an inflection point at 0 for two reasons. The first reason is that it doesn't change concavity, right? So even though the second derivative is undefined there, right, it doesn't change concavity, and it's not in the domain of the function, right? You divide by 0 when x is equal to 0. So there's actually two reasons. So those are my three answers, right? Concave up on this interval, concave down here, and we have an inflection point at x equals -3. All right, that's it for this video. Go ahead and take a break. I'll see you next time.